Okay, so Friday we talked about an experiment that compared SAT prep courses. So if you guys remember, it's the one at the top where we had 20 students. Some students were going to take an online course, some students were going to take an in-class course, and we were going to compare their improvement in SAT scores. Sound familiar? Yes. Okay. Next question. Let's say that I have those 20 students, and I know that 10 are in pre-calc, 6 are in algebra 2, and 4 are in geometry. What problem does this cause?
I don't know who you're pointing at.
You, because you were raising your hand.
Okay. Well, like when we talked about earlier, how like the researchers should control other variables. Like we can't be sure that the reason their score is like change or whatever because of the course, but it could just be the courses they're taking outside of this SAT prep.
Okay. What is the worst case scenario here? If we randomize our two groups, our classroom group and our online group, what's the worst case that could happen with these 20 students?
One group is all pre-calc.
One group is all pre-calc. So worst case would be that group 1 is all 10 pre-calc kids. And then group 2 is my algebra 2 kids and my geometry kids. Now, let's say that group 1 had a higher improvement in their SAT scores. Do we know that it's because of their treatment? No. Could be because they're in pre-calculus. So this is the worst case. Now, it's not likely that all 10 pre-calc kids would end up in the same group, but could it happen? Yes, for sure.
Why does that have to do with like their improvement though? Because like isn't like if they were in pre-calc before like the first test I took them in pre-calc too. So like why does this do their improvement?
So theoretically, the math class that you're in could have an effect on the improvement in your score.
Okay.
So it might be that pre-calc kids, because they're older, they pay more attention, and they're going to have a bigger improvement. Does that make sense? Okay, so that's worst case. In this case, we don't know if there's a larger improvement. We don't know if it's because of the treatment or because of the math class that they're in. So there's two ways that we can address the problem. First way is that we can eliminate, not include, the algebra 2 and the geometry kids. Now, what problem is that going to cause? Like, why might that not be ideal? You're going to have a smaller sample. That's true.
Like if they've learned more math throughout their years, then like they might have more concepts that they know on the SAT.
Right, but if I just don't include this, and I only look at pre-calc kids. Margo?
You can only like conclude stuff about like pre-calc kids. You can't say like, oh, geometry kids will.
Right, I can only make conclusions then about students that are in pre-calc. Now, in this case, I really can only make conclusions about who? These pre-calc kids, because they're what? They're volunteers. So I really don't want to just get down to only kids in pre-calc. But even if they were a random sample and I eliminated these two groups, I could only make conclusions about students in pre-calc. So that's not ideal. Second is called blocking. So this is what we're going to learn today. Before I tell you what blocking is, we're going to look at the results of this experiment. So here is the experiment. Here are 20 kids. This says what class they're in, what treatment they got, and what their improvement was. So what I want you to do right now is make 2 dot plots, one for each treatment. I would suggest you do something like this, that you use the same scaling, because ultimately we're going to compare them. What should be my lowest and what should be my highest? 0 and 100. Okay, I'm going to draw mine up here. You do the same thing. here's what mine looks like. Yours should look generally the same, except hopefully you didn't put the 50 in a bad spot and then use a pen. Okay, so does it look like there was an improvement? A significant improvement?
Yeah.
What if I ignore this kid?
Yeah.
I don't really think it looks like there was too big of an improvement. Maybe a little bit, but I don't think that it looks like there's a vast improvement. Now, the issue here is that we mixed all the kids together who were in these different classes. So we said it's possible that your improvement might be different based on the math class that you're in. So really what we should do is we should look at the math classes separately. What was the improvement for kids in the online pre-calc versus the classroom for pre-calc students? So that's what I did on the next page for you. If you go to the next page. Okay, so here, we still are comparing the classroom and online improvement, but it's broken up by courses. So these 2 squares, or the 4 squares really, those are the kids in geometry. So in this case, we can see there was a bigger improvement in the online course for just geometry students. The circles are the kids in Algebra 2. So there is a greater improvement in online for the Algebra 2 kids than for the classroom. These are the pre-calc kids. So I would argue that this shows much better that there is a larger difference in the 2 treatments for each group. Do we agree? This is the idea of blocking. So we're going to skip all of that because that's basically what I just said. Starting with, what is the benefit of blocking? Blocking accounts for sources of variability. Really a single source. So it's basically you're taking a confounding variable, and that's going to be what you block on. It's very similar to stratifying. Now, how do we determine which variable might be best to block? Okay, how do you determine which variable to stratify by?
It's a variable that means the groups within themselves are similar, but different from each other.
Okay, sure. So groups should be similar, like within the group. Claire?
They're relevant. Like, I mean, like if you like split the last thing up by like girls and boys, that wouldn't necessarily be relevant to their scores.
Relevant to what specifically?
So the response.
The response. Yeah. So you want to block by the variable that is most strongly associated with the response variable. The term I also used before was a predictor. So the math class that you are in is associated with an improvement in your SAT. Like Claire said, your gender is not associated with your improvement in the SAT. So gender would not be a good blocking variable. The caffeine experiment that we talked about, so where some people get caffeinated soda and some people get decaf soda, what could you block on in that case? So what is related, what was our response variable? On what? On your pulse. So what affects your pulse besides caffeine? Weight, sure. Stress, sure. If you're anxious all the time, yes. Victoria?
Your normal caffeine consumption.
Yeah. Your regular caffeine consumption. Those would all be blocking variables. So then the real question is, what's the difference between blocking and stratifying? They're pretty much the same thing. Blocking is the term that you use when you have an experiment. Stratifying is the term that you use when you are taking a survey. So I just remember blocking is almost exactly the same as stratifying. Serves the same purpose, just in a different context. Okay, if we go to the next page, we're going to talk about another example that has to do with blocking, or where we could use blocking. Popcorn lover wants to know if it's better to use the popcorn button on our microwave or use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and she buys 10 bags each of 4 different varieties of microwave popcorn, for a total of 40 bags. Outline a randomized block design for this experiment. First question, what are the blocks in this case? The variety of popcorn. So if we weren't using blocking, we would number each of all 40 bags, put the numbers in a hat, mix them up, draw 20 without replacement for one treatment, 20 for the other treatment. With me? Why would we choose to block in this case, though? Well, first of all, why would she have gotten all of these different types of popcorn? Why not just get one type? Victoria?
Because each of them will take a different amount of time to respond to the microwave.
Yes. What else? Grace?
Each might say a different time on the bag.
Sure. Each might say a different time on the bag. Emily?
Sizes of the bags, like it could be like 10 ounces or 20 ounces of popcorn.
Sure.
She like wants to know what's better to use for like popcorn in general, not just like the one kind.
Exactly. Perfect. If she only chose one type of popcorn, her conclusion can only be for that one type of popcorn. In this case, because she included 4 different types, whatever conclusion she comes to will apply to all 4 types of popcorn, as long as she has a random sample. That makes sense? Now, is it reasonable to believe that this is a random sample if she buys 10 bags from the same store? Definitely not. But if it were a random sample, she could make a conclusion about a much bigger population. Okay, so we have our 4 different blocks. The idea with blocking is that your experiment is done in each block. So what we need to do is we need to take our movie butter popcorn and split it up into 2 groups. One for the microwave, one for the time on the bag. Same thing with the light butter and the natural and the kettle corn. Does that make sense? With me? Okay, so first thing we need to do is we need to randomize. So I'm going to say number the bags 1 to 10 for each variety. Put all 10 numbers in a hat. 1 hat per variety. So I have a hat for movie butter, a hat for light butter, etc. Then what am I going to make sure I don't forget? Mix. So I'm going to draw half without replacement. And I'm going to pop using the microwave button. For the remaining numbers, pop these bags using the time on the bag. Okay, so do we all see that I'm outlining this for all 4 separate groups? What would I have to talk about next? So I've talked about my randomizing, I've talked about my treatment. Come on guys, be resourceful. If you stare at me, the answer's not all of a sudden gonna flash across my forehead.
Since you already have the numbers, all the data for the specific ones, would you average all of them to get a general?
Average what?
The time. Average the unpopped kernels in every bag, and then
Yeah, you skipped a step.
get a general.
Yeah.
I don't know what step
What are you counting? Yeah, exactly. So we are going to count the number of unpopped kernels in each bag. And then, like Alex said, we are going to compare the average number of unpopped kernels for the two methods for each popcorn variety. So I'm going to take average number of unpopped from the microwave time, average number of unpopped from the bag time for each of the 4 varieties and compare those two averages. That make sense? And then whichever one has the lower number of unpopped kernels was the more effective timing method. Does that make sense how you're going to write a block design? Do we get why we would block? What the purpose is? Okay, here would be my advice to you. Yes.
This is like not stats related, but like a flaw with the experiment here is like you just completely burn it and like.
Yes,
get, like,
I agree.
Yeah.
Totally agree. Yes. So this is assuming that your better treatment is the one that has the less number of unpopped kernels, but that also could mean that you just burned the bag. So yes, I agree. You would have to take that into account somehow. Anyway, do we get why we would block? Grace?
So should you say whichever method has like fewer unpopped kernels total across the 4 or fewer average unpopped kernels?
I would compare the averages for each block, because it could be that your results change when you look at a different block.
So you'd have a different, better method for each 4 blocks.
Right. Ideally, it would be the same, but it's possible, yes. Okay, here would be my advice. It's possible to block in every experiment. I would only block when you're asked to. So sometimes you'll be told something like, this is a confounding variable. How would you control it? Well, I would block. Or would blocking be appropriate? I would not just throw blocking into every single experiment. I would only put it in experiments where it really makes sense. You with me? Okay, we have one other design we need to talk about. It's called a matched pairs design. Matched pairs design is kind of like a blocked design, but your block only includes 2 units. Generally, your 2 units are 2 similar people or the same person. Okay, for example, let's say that I want to compare 2 different mosquito repellents. What I could do is I could choose half of you randomly to get one mosquito repellent, choose the other half of you randomly to get the other repellent. I would send you outside, bring you back in after 10 minutes, and we would count how many mosquito bites you got. That is a randomized design. If I wanted to use a matched pairs design, each of you, so the same person, each of you could be your own block. That would mean that each of you have to get both repellents. How could I give both repellents to each of you? Half your body. Probably one on each arm. So you would get one repellent on one arm, one repellent on the other arm. You would go outside, come back in, we would measure the number of bites. What is the advantage to that?
Each person might have like a different attraction. Mosquitoes might bite them more, and somebody might get bites.
Yeah. Yeah, and we all have seen that. There's some people that get a lot of mosquito bites, some people who don't get very many, and some people who are in between. So then we could really see what's the difference for you personally. Does that make sense? So that would be the same person. Similar to people, a lot of times that's used for like twins. If you take a set of twins, one person gets one treatment, one person gets the other treatment. Now, what are the 3 requirements for every experiment? Not designing an experiment, but what do you have to include in every experiment? Randomizing, control, replication. So in the case of the mosquito repellent, what does it mean for me to randomize? Or how would I randomize?
Which side of the body?
Yes, you have to randomly determine which side of the body gets which repellent. Theoretically, maybe your left arm just naturally gets more mosquito bites. Ridiculous, I know. You have to randomize though. So you have to randomly determine which arm gets what treatment. Does that make sense? Okay. One other real quick example. Let's say I'm comparing two different types of shoes, and I want to know which shoe makes you run faster. What could be my matched pairs design? So I could have you all wear both pairs of shoes, sure. What would be a good blocking variable though? What relates to how fast you run besides the shoes that you're wearing?
Like, you could get like track athletes that have like the same like time that they run like a certain race. Does that make sense?
Yes, it does. Thank you, that brought up something for me. You can never block on the response variable. So if I'm looking at how fast you run, I can't block you on how fast you run. Claire?
Gender, because you're looking at strength difference.
Sure, maybe gender.
Height.
Could we go with height? Because that'll be easier for me to show you what I mean. Okay, so it's reasonable to believe that height has a relationship with how fast you run. I mean, it's not the sole determined predictor, but it's related. So what I would do in the case of a matched pairs design is I'm going to pair up the two tallest people all the way down to the two shortest people. Then in my block of every two, I'm going to randomly decide one person gets one pair of shoes, the other person gets the other pair of shoes. So then I will compare within each of those matched pairs. Does that make sense? Okay, do we get the idea of matched pairs then?
Yes.
Okay. That was the end of chapter 4 notes.
All right.